In this lecture, we derive the thermodynamic properties of the black zero-brane from M-theory and its low-energy limit, 11-dimensional supergravity, using only supersymmetry as input, no details of the dual-gauge theory. We start with the classical M-wave solution, reduce it to 10 dimensions, and then include quantum gravity corrections via higher derivative terms, the r to the fourth contributions. From the corrected geometry, we obtain explicit formulas for the temperature, the entropy, the energy, and the specific heat. At low temperature, the specific heat becomes negative, signaling a thermodynamic instability associated with Hawking evaporation. In the next lecture, we will compute the same thermodynamic quantities directly in the BFSS-10 matrix quantum mechanics using Monte Carlo methods and compare them with the supergravity and M-theory predictions for the black zero-brane. Viewed through the duality, these results function as both prediction and verification of quantum gravity. On the gravity side, the thermodynamic scalings and the subleading corrections, 1 over n squared and alpha prime, are quantitative predictions. On the gauge side, finite n Monte Carlo in the BFSS-10 matrix quantum mechanics provides an independent non-perturbative check. This is a sectorial test, near extremal d0, large lambda, thermal, Euclidean, but within this window it gives a sharp and controlled confirmation. We begin on the M-theory side with 11-dimensional supergravity, the low-energy limit of M-theory. The field content consists of the metric GMN, the Majorana gravitino psi m of spin 3/2, and the three-form potential AMNP, whose field strength is the four-form F4 equal to dA3. The bosonic action, denoted S11, includes three main terms: the curvature R, the kinetic term for F4, and the Chern-Simons coupling A3 wedge F4 wedge F4. These terms together describe the classical dynamics of 11-dimensional supergravity. This is given in equation 1. Equation 2 expresses the 11-dimensional Newton's gravitational constant in terms of the Planck length Lp, the fundamental constant that sets the scale of quantum gravity in 11 dimensions. This scale will persist as we reduce to 10 dimensions and defines the framework for all subsequent thermodynamic quantities and quantum corrections. Before compactifying, we confirm the supersymmetry balance by counting on-shell degrees of freedom. The graviton contributes 44 components, and the three-form AMNP contributes 84, for a total of 128 bosonic degrees of freedom. The Majorana gravitino psi m provides 128 fermionic degrees of freedom, showing an exact one-to-one match between bosons and fermions in 11 dimensions. We now compactify on a circle, denoted S1. M-theory compactified on a circle of radius r is equivalent to type 2a string theory in 10 dimensions, with the string coupling given by GS equals r over square root of alpha prime. Here, alpha prime is the string slope parameter that sets the string length scale. Through this reduction, the 11-dimensional fields reorganize into the 10-dimensional sectors of type 2a supergravity. The metric GMN, the dilaton phi, and the 2-form B2 form the NS-NS sector, while the 1-form A1 and the 3-form C3 form the RR sector. This correspondence shows that the M-wave solution of 11-dimensional supergravity, which carries momentum along the compact direction, becomes the black zero-brane solution of type 2a supergravity, the gravitational dual of the BFSS matrix model. We now turn to a specific classical solution of 11-dimensional supergravity, the M-wave. This is a purely gravitational configuration, meaning the three-form field A3 is set to 0. The M-wave carries momentum along the compact direction x10, and its metric is shown in equation 5. It involves three main functions, f, h, and the radial coordinate u. The function f is defined as 1 minus u0 to the power 7 over u to the power 7, where u0 encodes the non-extremality of the solution through the parameters u plus and u minus. The harmonic function h scales as ls to the power 4 times u minus to the power 7 over u to the power 7, with ls the string length. Together, these functions determine the geometry and the redshift structure of the M-wave spacetime. Physically, the M-wave represents a gravitational wave in 11 dimensions carrying Kaluza-Klein momentum along the compact circle. When we perform dimensional reduction along this direction, we obtain the 10-dimensional non-extremal black zero-brane, or d0-brane solution of type 2a supergravity. This reduction maps the momentum charge of the M-wave to the Raymond charge of the d0-brane, establishing the precise link between the 11-dimensional and 10-dimensional pictures. We now describe explicitly the compactification procedure that connects 11-dimensional supergravity to type 2a supergravity in 10 dimensions. This is achieved by reducing the theory on a circle, denoted S1, along the compact coordinate x10. Equation 8 shows the Kaluza-Klein ansatz for the 11-dimensional metric. It separates the higher dimensional line element into two parts, the 10-dimensional metric GMN, which couples to the dilaton phi through the exponential factor e to the power minus 2 phi over 3, and the compact direction x10, which appears with the exponential factor e to the power 4 phi over 3 and the vector potential am. This vector potential becomes the Raman-Raman one-form field in type 2a supergravity. Next, the three-form field A3 decomposes as shown in equation 9. Its purely 10-dimensional components AMNQ form the Raman-Raman three-form C3, while the mixed components A10MN give rise to the NS-NS two-form B2. Thus, the reduction naturally produces both the NS-NS and RR sectors of type 2a theory. Finally, after integrating over the compact direction, the 10-dimensional action takes the form written in equation 10. It consists of the NS-NS part, the RR part, and the Chern-Simons term that couples B2 and F4. The resulting theory is type 2a supergravity, the precise low-energy limit of type 2a string theory. We now apply the dimensional reduction explicitly to the M-wave solution. Equation 12 summarizes the dictionary between M theory and type 2a supergravity. It relates the gravitational constants, the Planck and string lengths, and the compactification radius. The 10-dimensional Newton constant G10 is obtained by dividing the 11-dimensional constant G11 by 2 pi r. The Planck length Lp and the string length Ls are connected through the coupling Gs, according to Lp equals Gs to the power minus 1/3 times Ls, and the circle radius is r equals Gs times Ls. These relations establish how all physical quantities in type 2a theory inherit their scale from M theory. In equation 13, we show the 10-dimensional metric obtained by reducing the M-wave along the compact direction x10. It has the structure of a non-extremal black zero-brane solution in type 2a supergravity. The metric involves the harmonic function h, the blackening function f, and the radial coordinate u. The dilaton field is given by e to the power phi equals ls to the power minus 3 times h to the power 3/4, and the Raman-Raman one-form potential A is proportional to h inverse dt. This solution represents a charged black hole in 10 dimensions carrying d0-brane charge. In summary, the M-wave of 11-dimensional supergravity reduces directly to the black zero-brane of type 2a. Momentum along the circle becomes d0-brane charge, and the 11-dimensional gravitational wave becomes a 10-dimensional black brane solution. Having obtained the 10-dimensional black zero-brane from the M-wave, we now examine its near-horizon and extremal limits. In this regime, the solution simplifies, and its thermodynamic quantities can be expressed directly in terms of the gauge theory parameters. In equations 15 and 16, we define the harmonic function h and the blackening function f in the extremal or near-horizon limit. The function f takes the standard black hole form 1 minus u0 to the power 7 over u to the power 7, where u0 determines the position of the horizon. It is given in terms of T-Hooft coupling lambda and the parameter delta, which tracks the energy of the configuration. Indeed, delta measures the excitation energy above extremality. In the limit Ls going to 0, we keep the ratio delta over Ls to the power 4 fixed, which scales proportionally to lambda times the energy density E over n squared, as shown in equation 17. Thus, this relation connects the supergravity parameter delta to the energy density E in the dual gauge theory. The mass and charge of the black zero-brane are given in equation 18. This expresses the total energy and d0-brane charge of the solution in terms of the microscopic parameters of the BFSS model. Hence, in this near-horizon picture, The geometry corresponds to a charged black hole in 10 dimensions, whose extremal limit captures the bound state of d0-branes at zero temperature, while small deviations controlled by delta describe finite temperature excitations of the system. We now move beyond the classical supergravity approximation and include the leading quantum gravity corrections. The corresponding effective action is constructed by requiring local supersymmetry while adding higher-order curvature terms to the classical 11-dimensional supergravity action. When the theory is dimensionally reduced, these terms reproduce the one-loop effective action of type 2a string theory. For the M-wave background, only the graviton sector contributes, since the three-form field A3 is set to 0. The leading correction comes from 4 graviton scattering processes, which generate quartic curvature terms of the form r to the power 4. The coefficients of these terms are fixed uniquely by local supersymmetry and by matching to string scattering amplitudes. In equation 19, we show the resulting quantum-corrected M-theory action, written in terms of the curvature scalar r and the quartic curvature corrections, multiplied by the small dimensionless parameter gamma, which is proportional to lambda squared over n squared. This parameter controls the size of one-loop corrections and is directly related to the inverse square of the number of colors on the gauge theory side. The two tensor structures appearing in the correction, T8T8R4 and epsilon11R4, encode distinct contractions of 4 Riemann tensors. Together, they describe the leading deviation from classical supergravity. With the quantum corrections determined, we now examine their effect on the M-wave and its reduction to the black zero-brane. In equation 20, we present the quantum-corrected 11-dimensional metric. It maintains the same overall structure as the classical M-wave, but includes correction functions h1, h2, h3, and f1, which encode the higher derivative effects. Each of the harmonic functions, hi, differs from the classical h by an additive term proportional to lambda cubed over n squared, multiplied by the coefficient hi. Similarly, the function f1 receives a correction proportional to lambda squared over n squared, multiplied by the coefficient f1. These terms represent the 1 over n squared quantum gravity corrections to the geometry. When we reduce this corrected M-wave to 10 dimensions, we obtain the quantum-corrected black zero-brane metric, given in equation 22. The quantum-corrected dilaton field phi and the Ramond-Ramond one-form potential A are given in equation 23. Finally, the location of the horizon shifts slightly due to the correction, as expressed by the condition F1 evaluated at the horizon equals 0. This implies that the ratio UH over U0 deviates from unity by a small 1 over n squared correction proportional to F1. Thus, the higher derivative terms not only modify the geometry, but also shift the horizon and temperature of the black zero-brane, producing measurable effects in its thermodynamics. We now compute the thermodynamic quantities of the quantum-corrected black zero-brane. These quantities are obtained by evaluating the corrected geometry near the horizon using standard gravitational thermodynamics and the Wald entropy formalism. The temperature is derived by removing the conical singularity from the Euclideanized metric. Equation 24 shows that the Hawking temperature is proportional to h1 at the horizon to the power minus 1/2 times the derivative of f1 at the horizon. When written in terms of the dimensionless variables tilde u0 and tilde t, the result becomes tilde t equals a1 times tilde u0 to the power 5/2 times the quantity 1 plus epsilon times a2 times tilde u0 to the power minus 6, where epsilon equals gamma over lambda squared. This expression encodes both the classical scaling and the leading 1 over n squared quantum correction. The entropy is obtained using Wald's formula, ensuring that the first law of thermodynamics is satisfied. The result is given in equation 25. Finally, the energy and specific heat follow from the first law, dE equals TdS. They are given in equation 26. The second term, which carries the negative sign, represents the one-loop quantum gravity correction to the thermodynamics. These results show that quantum effects reduce both the energy and the specific heat at low temperatures, leading to deviations from classical supergravity that can be compared directly with lattice Monte Carlo results from the BFSS matrix model. In particular, at sufficiently low temperature, the negative correction term dominates, and the specific heat becomes negative. This signals a thermodynamic instability of the black zero-brane, corresponding to the onset of the Hawking evaporation process. In the large N limit, this instability disappears, and the system returns to a stable classical black hole phase, consistent with supergravity expectations. In this lecture, we have derived the thermodynamic properties of the black zero-brane analytically, starting from the framework of M-theory and its low-energy limit, 11-dimensional supergravity. Our construction relied solely on the fundamental requirement of supersymmetry without invoking any details of the dual-gauge theory. In the next lecture, we will approach the same problem from the opposite side of the duality. We will compute these thermodynamic quantities directly from the gauge theory perspective, using the BFSS 10-dimensional matrix quantum mechanics, and show how the results match precisely with the predictions of the black zero-brane in supergravity and M-theory.